Hello students, this is Dr. Ben. I'd like to work on a problem out of the last part of Chapter 5 that has to do with circular motion dynamics, but it considers a track. In this particular case, it's a flat track. Alright, so let's make a list of what we know about this problem and what we want to find. So the object of interest is a car, and we're told that the coefficient of static friction between the car and the road surface is 0.6. Alright, the mass of the car is given to be 1,000 kilograms. The radius of the curve that the car is going around is 50 meters. And we might as well use our approximate value of g on the Earth, 10 meters per second squared. And what we want to find in this problem is the speed that the car can go around the corner and not slip. So this is going to be velocity, but it's actually going to be the maximum amount which would occur when the friction has its largest size. Alright, so this is uniform circular motion that occurs in a horizontal plane. So usually in problems like this, it's best to draw both a top view and a side view of the situation so we can see everything that's going on. So let's draw the top view of the situation. The path of the car would look like a circle, and just for convenience, let's put the car over here and pretend that its velocity is in that direction, and the center of the circle would be to its left, and the circular acceleration is going to point towards the center, which would be to the left in this point of view. Alright, and then if we draw a side view, so we'll let that straight line represent the ground, and we'll put the center of the circle over to the left as our top view shows, and we'll put the car over here to the right. And so if I draw the forces that act on the car, then the vertical forces are the familiar weight and the normal force, but there is an inward force caused by friction in order to keep the car from sliding outwards, and that's going to point towards the center of the circle in the direction of the circular acceleration. Alright, so this is a force and motion problem. We have to use Newton's second law, a little bit of information about circular motion kinematics, and we're also going to have to go back and use our model of friction so we can find the relationship between the frictional force and the normal force. Alright, so let's do the circular motion dynamics part first. So let's start our analysis by using Newton's second law. So we'll say that the acceleration is equal to the net force divided by the mass. And I better put a coordinate system in this side view so I get my directions right. So let's call the y direction as up, and let's call it the x direction pointing towards the center of the circle. Alright, so if I solve Newton's second law in the x direction, then that would tell me that A sub c would equal the net force in the x direction divided by the mass. Alright, the centripetal acceleration A sub c I can write as v squared over r, and then that would equal the net force in the x direction is only the static frictional force, as there are no other x forces that we see in this problem, and that would be divided by the mass. And my ultimate goal is to figure out what this velocity is, and that would be our target. And so in order to do that, I need to figure out what is the size of the frictional force. Alright, so in the vertical direction, this car is at rest, so the net force in the y direction equals 0. So that means that the normal force minus the weight equals 0, and the normal force equals the weight. and recalling that the maximum value of the static friction is the coefficient of friction times the normal force, we can put all these pieces together in order to come up with the relationship for the speed. Alright, so I have V squared over R is equal to the frictional force, which is mu s times n divided by the mass. Alright, so the normal force is equal to m times g, and divided by the mass. So I put my left hand side there, v squared over r. And you notice that the masses cancel out in the numerator and the denominator. So I have v squared over r is equal to mu s times g. And if I solve this for v, I get v squared equals mu s r times g, or v is equal to the square root of that mu s r times g. Alright, so if I move my paper up a little bit, we can actually figure this out numerically. So it would be the square root of 0.6, which was the coefficient of friction that was given, times the radius of the curve that was 50 meters, multiplied by g, approximately equal to 10. So we have 50 times 10, which is 500, times 0.6, which gives us 300. So we have the square root of 300. 300 square root gives me 17.3. So the speed would be equal to 17.3 meters per second. And I think I'm only going to keep two significant digits here because of the numbers that were in the problem. So I'll go ahead and round that to 17 meters per second. So I'll double check that I have my units and I have my significant figures. And so what we found was the maximum speed of this car going around the corner, 17 meters per second, which is around 35 miles per hour. Because there's approximately 2 miles per hour in every meter per second.